And then so then what was our voltage across our load? Yeah, what was our voltage across the load? And this is another, see, because when we had it over here, and I can see why he got confused, because it looked like we were actually calculating out the voltage across the load, but this is Thevenin's voltage. So be careful of that when you're doing your worksheets. That's kind of just a separate thing. I brought it over here because this is where we remove the load to calculate all that stuff out. But it's not really the actual load. I'll have to move that around and change that up a little bit next year. So what was the voltage then across the load then? You had to find the voltage across the load for calculating out the current, right? So again, you could either go ahead and you could add them up, add them together, and divide by the thing and get the current, or you could just use our voltage divider formula.
2.975 volts.
2.975 volts.
I got it.
And if we get our voltage and we know our resistance, we can know our current. And what's our current?
5.313 milliamps.
5.313
313.
milliamps. Okay, you want to agree with that then? Everyone get the same answer? Anyone have any questions on any of the steps? I think the biggest one here is determining the resistance by the load. That's where we replace that with the voltmeter. Remember, and just replace it with an ohm meter. Treat your ohm meter as the power supply. Short this one out, and then redo your circuit. If you remake your equivalent circuits, it becomes a little bit easier.
How do you get the voltage for the R load right over again?
Well, because we know this resistance and we knew this resistance, right? So maybe we can just use our voltage divider formula, and it's going to drop proportionally across the two.
Okay.
Yep, and then just use your voltage divider formula, calculate out what that voltage is across that resistor, and then you can just take that voltage divided by your resistance and get your current. So definitely practice these. One of these are on the final. So, okay. So
Which one?
Make sure you practice these up. Anyone have any questions on it, knowing that it's on the final?
This
Everyone
one?
good with it?
Which one's on the final?
Yeah.
We figured out RTH, the 1.84 kiloohm.
Yep.
Which is the formula for that? I thought it was the 1 divided by R1.
Nope. Okay. Well, so first of all, so to figure out the RTH, that's this step right here. Okay. So let's just draw that one up. That one is the most complicated one. So we're going to just replace this with an ohm meter. Okay. Now our ohm meter is kind of just like a power supply. So if I'm going to put this one as positive, negative, all my current is going to come on in my ohm meter. It's going to go through the grounds. Some of the current's going to go this way. Some of the current's going to go through this way, and I got my shorted out power supply here. And this current's going to go through here. Then it's going to join in at this point here. And those two currents are going to combine and go through R3 and then back into my source, which is what I consider my ohm meter. Okay? So now if we redraw that up, so I'm going to draw my source as my ohm meter. Got my positive and negative. So I'm going to come down, I'm going to go, and then I knew that I'm going to split. I mean, it came down, I tied all my grounds together, I'm going to split. Some of my current's going to go through R2, and some of it's going to go through R1. So I'm going to force myself to go up, I'm going to force myself to split. And then some of it went through R2, some of it went through R1. So R2 and R1, and then those two kind of combined back together. And then that all goes through R3. And then R3 goes back into my ohm meter. So now if I hook up my ohm meter, and basically all I'm doing is I'm measuring my resistance across these three resistors. But to calculate all my three resistors, I need to get my equivalent circuit. So what is that? R3 is 120?
820.
820. R2 is 6 kilo ohms. 6.8 kilo ohms. R1 is 1.2 kilo ohms. Okay. So what you want to do is you want to combine, figure out what that total resistance is. That would be just like me putting an ohm meter across all three of these resistors. I combine these two resistors in parallel, so I know that it's going to have to be less than 1.2 kilo ohms. So what's my parallel resistance for R1 in parallel with R2? What does that equal?
1.02 ohms, or kilo ohms.
1.02
Kilo ohms.
kilo ohms. Okay? Now I combine those two, that made that into one resistor, right? Now I would have myself a series circuit, right? Like just combine these two and made it into one.
Like I get how to, I mean, when you add them in a series here, but when you're doing the parallel, that's where I have the problem.
Okay, so remember our parallel formula then is our RT is equal to 1 over R1 plus 1 over R2. Okay, or however many resistors you have in parallel, you just do the inverse. You know where your inverse key is on your calculator is?
Yeah.
Okay, so what you're going to do is you're going to put in R1, you're going to put in 6.8 kilo ohms, hit the inverse, hit your plus sign, do 1.2 kilo ohms, hit the inverse, hit your equals, and then hit your inverse one more time, and then you should end up getting this answer here.
That's where I was messing up.
Yep. Yep. And then now you have to do, now we have a series circuit. Now all we have to do is add 820 ohms to that 1.2 kilo ohms, and then you should end up with your Thevenin's resistance of 1.84.
What happens to that first resistor though? In the circuit.
What's that?
What happens to the first resistor in the circuit?
This one here?
No, on the far left.
This one here?
Yeah.
That's this one right here. Yeah, see, it doesn't look the same after we change out when we change the circuit up. Because remember, we shorted this power supply out, so that just becomes a line now. We're using our ohm meter as our source, and we reconfigure it. It's kind of like, it all depends on, it's kind of, I think in the book they say something that's all about the point of view that you're looking at it from. You know, whether if I'm looking at it from the load, or am I looking at it from the power supply. Okay, so if I'm looking at this circuit in the view of me being the load, I'm going to see it a lot differently than if I was the power supply and looking at the circuit. That make sense? All right, here's my little favorite analogy. All right, so we got two viewpoints. One looking at it is from the as if we're the power supply looking at the circuit, or if we're the load looking at the rest of the circuit. So, for example, we'll here's Tom's house here. Okay, and then Tom lives in a neighborhood, so Tom has neighbors.
Is that good or bad?
Okay, so Tom has, well, we're going to find out here really quick. Okay, so here's Tom's house, and then here's all his neighbors. So Tom is the power supply, okay? So Tom looks out his window and he sees his neighborhood. He says, "Oh, what a great neighborhood am I living in?" Okay, this is just a wonderful neighborhood. Okay, now we look at this neighbor. He's the load resistor here, okay? And he looks out his window and he looks right across over at Tom's house and he goes, "Holy crap, look at what I got for neighbors. Look at this neighborhood." So it all depends on which way we're looking at it. You know, Tom's looking at it and saying, "Yeah, this is a wonderful neighborhood." This neighbor looks over towards Tom and he says, "Oh man, I got some really crappy neighbors." So it all depends on which way we're looking at it. So this is kind of like, here's the power supply looking out at the neighborhood, and this would be the load resistor looking at the rest of the circuit. Okay, so that's how it's all based on the viewpoint. Whatever the viewpoint is. So here's the load looking at that circuit. Then that's going to be a different circuit than what the power supply sees. Does that make sense?
Yeah.
Yeah, so it all depends on the viewpoint. And so then you have to re-sketch it all out. Yeah, that's a Tominism.
Tominism.
We got a bunch of them. All right. Any other questions on Thevenin's theorem? It's only 3 resistors. Can't be that tough. Again, like I said, though, it's the basic circuit, but the complexity of what we're actually doing is what we're trying to get at. How are we looking at that? How are we looking at it? Yeah, try them, and then we'll be in lecture again on Monday. So, if you have any questions on any of your worksheets, bring them up while you're trying to do them. Like I said, this one will be on the plan. All right, let's before we run out of time here, we're going to do the super fast mode on superposition. Superposition. Then we'll do the troubleshooting maybe we'll let you do a couple of your labs here first so you get to understand series parallel circuits. So maybe we'll do like troubleshooting maybe like on Wednesday or something like that. That way we can get a little bit of lab time in before we do the troubleshooting. All right, so again, if we just follow the procedures, we can solve for all these. We can solve for all these answers just by following the procedures. Now here's the procedure. But what's really going on is what we really need to know. So when we're working with superposition, what happens is that when we're working with superposition, it means that we have 2 sources going in there. Well, when we're looking at these sources, this source doesn't even realize that this source is in there. It's just a direct short for it. And so that circuit looks different than what this source is going to look at this circuit at. And where this really comes into play is when we're working with solid-state devices. Because we're going to be powering up our solid-state devices with DC power supplies, but our signals are going to be AC. And our AC signals are going to go ahead and change our whole look of our circuit because of the superposition. The AC signal isn't even going to see that this power supply is right there, and it's going to go ahead and go through the whole circuit, and it's going to be, the AC is going to look at it as a completely different circuit. For example, if I had a superimposed AC signal right in series with this power supply, it would ignore that this power supply is even there. That AC signal would go through, and it would look at the circuit differently than what the DC one would. And we see that when we get into solid-state devices. So when we get into solid-state devices, all of a sudden I'll bring up superposition again. So that's what we're really kind of taking a look at is how do I analyze a circuit that has both, when we get into solid-state devices, both an AC and DC circuit. Here we can just do it with our DC sources and it acts the same way. So what it says is that replace all but one of the voltage sources with a short. Current sources are replaced with an open. Okay, we can have 2 different types of sources. All our sources that we use out in our labs are all voltage sources. When we get into solid state, we're going to talk about current sources coming up. That's where it remains a constant current. No matter what's going on with the load, it's going to remain a constant current. Here, we have voltage sources that, no matter what I do to the load, it always maintains a pretty specific voltage unless we really load the thing down. But voltage sources are regulated voltage sources, and we always maintain a certain voltage. Current sources are ones that maintain a certain current going through the load, no matter what the resistance is. All right, so it says replace all but one of the voltage sources with a short. So we're just going to go ahead and we'll just short out. It doesn't matter we can do number 1 or number 2. So we'll just go ahead and let's do number 2. So we're going to remove our power supply. So in your lab, you're going to go ahead and remove the power supply and then put a short where you remove the power supply. Now it gets to be a little bit tricky in the DAC, but you'll have to try figuring that out. It gets a little bit tricky. Some of these superposition ones, you might want to use the regular DC power supplies so you understand the concept of it. All right, then so you replace one, and then it says solve for the currents flowing through each resistor. Okay, so then again, we have to re-sketch out our current path. So here I got all my current coming down, all my grounds are connected. So I'm going to come up to the first current node, some of my current's going to go through R3. Some of my current's going to go up through the power supply right through it. It doesn't even see that that power supply is in there, even though it is. Then it's going to come up into R2. And then the current of R3 and R2 are going to combine. And all the current is going to go through R1. And then back into my source. So then if we rough sketch out our equivalent circuit, got all my current. My current's going to go up. It's going to split off into two different directions. I force myself to go up. Some of it's going to go through R3. Some of it's going to go up through the power supply, which is just a short, so that's just a piece of wire, and into R2. Then those two currents are going to combine and then join in with R1. So R1. They're all in too up. Nice easy ones. All right, so we have everything in there.
Voltage.
Voltage, what's my voltage?
It's 12.
12. Okay. Current path and polarities, again, they're by avoiding, sometimes I'll skip that, but you shouldn't. It's good practice. All right. So then it says solve for the current that's flowing through each resistor. Okay, so we already did that. Okay, so now we need to calculate out how much current is flowing through each resistor. We already determined the direction of the current. And so it says, let's see, solve for the currents flowing through each resistor. So again, we got to reduce it down to at least this series circuit. We're going to do some shortcuts here a little bit so we don't save ourselves some time. So I can combine R2 and R3 together, right? So then my equivalent circuit's going to look like so what's my resistance of R2 and R3? 500 ohms. See, so we can start doing some pretty quick shortcuts now. Okay, then we're going to draw in our current paths and polarities. All right, so and we know that we have a 12-volt source. How much voltage is R1 going to drop more than our R2 and 3? Going to drop twice as much, right? So we know that this one here would have to be 8 volts. This one's going to have to be how much? 4 volts. If I add them all up together, I get my 12 volts. So I know that R1 is dropping twice as much voltage as R2 and 3. All right, now all we have to do is determine what the current is. So what's my current going through R1?
8 milliamps.
8 milliamps. Okay, how much current is going through R2 and 3?
8 milliamps.
Better be 8 milliamps. Is what remains constant in a series circuit?
Current.
Current. Yeah, so it better be 8 milliamps. All right, so now we have all that information. Now we got to transfer it over into our main circuit. So how much current is going to be going through R3?
4 milliamps.
4 milliamps, half the current, because we have all our current going through it, and then it's going to branch off. So that means, and since the resistance are equal, that means we can do 4 milliamps across each one. Okay, how much current is going through R1?
8 milliamps.
8 milliamps. Okay, how much voltage is going across R1?
8 volts.
8 volts. How much voltage is going across R3? 4. Because what remains constant in a parallel circuit? Voltage. So all we have to do is just take this voltage here and transfer it over to both of them. Alright, so we have all our information that we need. So our first step was R1 was 1 kilo ohm. Our voltage of R1 was 8 volts. Our current going through it was 8 milliamps. Our second one was 1 kilo ohm, 4 volts, 4 milliamps. Oh, I'm sorry. Don't do it there.
No, no.
Sorry about that. I'm still in R1. We're trying to do the express version of the superposition. 1 kilo ohm, 4 volts, 4 milliamps. All right, and then R3 was here. That was 1 kilo ohm, 4 volts, and 4 milliamps. There we go. Okay? And we know that the current going through R3 then is this way, and then R1, so we have all our currents for our first step. Okay, so we took care of the first step. Now what you want to do is you want to change up colors because you don't want to lose. So you might want to get yourself some colored pencils, but you don't want to lose these current paths for the first step. You want to keep those current paths in there in polarities because we're going to need that on our last step. All right, so now so we're all done with this one. Erase this one. And then we're going to do it again. Now this time we're going to go ahead and remove this one and short out this one. This time we have 24 volts and my current is, now this time my current is going from negative to positive, so now this time my current is going this way. So it's going negative, positive, then it comes up. Then it's going to split. Some of my current's going to go this way. The remainder amount of current's going to go this way. Through my short. Into this current node here. Those two currents are going to combine, and then now my current is going to go back into my source. Okay, so that's going to be my polarity of my second path. Everything in red now is my polarity across my components in the red. And then we'll come back to that and take a look why we need that information. Okay, so then we have to re-sketch out our this time our power supply is upside down. Good practice just to go from negative to positive. So this time all my current is going to come up. It's going to go through R2. This time we're going to go work our way down. So here's R2. All my current is going to go through R2. Then it's going to split. So I force myself to split. Some of it's going to go through R3, and some of it's going to go through R1. So some of it's going to go through R3, some of it's going to go through R1. And then those two currents are going to combine and go back into my positive side of my source. Okay, we have a 24 volt source. Okay, and R2 is 1 kilo ohm. R3 is 1 kilo ohm.
1 is 1 kilo ohm.
Okay, so now we just have to do the same thing. So my equivalent circuit is going to be so this is going to be R2 this time. This one's going to be the combination of what?
R3 and R1.
R3 and 1 parallel. Okay? So R2 doesn't change. That's still going to be 1 kilo ohm. R3 and R1 being in parallel together gives me what? 500 ohms. Okay, so got 24 volts. So what's my, so either I can use my voltage divider formula, or I can add my total resistance and calculate out my current. But let's find our voltage first. So how much voltage am I going to get across R2?
16 volts.
16 volts. That's going to drop twice as much as R3 and 1 being in parallel, because that's only 500 ohms, so that means that the remainder must drop how much? 8. Okay, now we can calculate out our currents. How much current do I have going through R2?
16 milliamps.
16 milliamps. And how much current do I have going through R3 and 1?
16 milliamps.
8 milliamps.
Who said 8?
Oh, sorry, I did it a different way.
Yeah, it's a series circuit. There is no other way.
Yeah,
Oh, you already divided it up?
Yeah.
All right. All right. Good. All right, so now I got a total current of how much total current? What's my total current of this circuit?
16 milliamps.
16 milliamps. So I got 16 milliamps coming through. All the 16 milliamps is going through R2. Then it's going to divide up. Some of it's going to go through R3. And how much is going to go through R3? 8 milliamps. The other half of that 16 is going to drop across R1, and that's going to be our 8 milliamps. And then those two currents are going to combine. So I get my total current of 16 milliamps again, and then back up to my source. Okay, so be careful, watch out for, also I might switch up one of these power supplies on one of your circuits, so make sure you don't constantly always assume that it's always going to go counterclockwise. All right, and we got 16 milliamps here, and we got a voltage of 16 volts here, and we had a voltage of what across R3?
8 volts.
8 volts. All right, so now we have all that information. So R1 was 1 kilo ohm, 8 volts, 8 milliamps, R2. R3, then it's 1 kilo ohm. All right, so now what we have to do is determine, because we can't have currents flowing in opposite directions in any given circuit. So then it becomes, who's the bully of the block? Then we want to grab our third color, and we want to just kind of find out what is the difference between the two. So we know that we have, so how much difference do I have between, yeah, I don't have any difference between them. My currents across R1 are both going in the same direction, right?
Yep.
So I'm going to just have I'm going to get the same amount of voltage going across that, and I'm going to get my same amount of, I'm going to have 16, I'm going to have 16
Million.
So I'm gonna have twice as much voltage and twice as much current. So I'm gonna have 16 volts being dropped across that one, and I'm gonna have 16 milliamps of current. I'm just gonna add those up. If the currents are going both in the same direction, then I'm just gonna add them up. So I'm gonna get twice as much current because I'm gonna get the current from this power supply, plus I'm gonna get the current from this supply. So I'm gonna get twice as much current going through this resistor. And if I have twice as much current going through it, that means I'm going to have twice as much voltage drop because R stays constant, and if I increase my current, so does my voltage. So now I'm going to get 16 volts going across R1 at 16 milliamps. R2 is the same thing. I got 16 milliamps, both going in the same direction. Those two are going to add up, so now I'm going to end up with 32 milliamps of current. So what's that going to give me for voltage? I get 32 volts.
20 and 20.
20.
Oh, 20, sorry. Yeah. Got one of my, yeah, Delvin. Sorry. Good catch. Like I said, all I see is just a little bit. So 20 milliamps, I add those two currents up and we get 20 milliamps. And then my voltage is going to be what?
20 volts.
20 volts. And my total resistance is still going to just be 1 kilo ohm. That stays constant. All right, so those two currents are both going in the same direction. So those two currents and those voltages just get added up. Now I get down to R3 here. Now I got currents that are going in opposite direction. And remember, it's always the biggest bully on the block is always going to win, right? So is my current going to be going through R3 going to be going from north to south or south to north?
North to south.
North to south. It's going to be this one right here that's going to win. This one has twice as much current as what this one does. But this 4 milliamps is still going to be opposing that 8 milliamps, and so I got them going in the opposite directions. So what's that going to leave me for current going through R3? 4 milliamps. If I have 4 milliamps going through my 1 kilo ohm resistor, what's my voltage going to be across it?
4 volts.
And I'm going to get my 4 volts going across there. Okay? So when we're looking at this power supply doesn't even see this power supply. This one doesn't see this power supply, but they're both feeding into that same circuit. They both see R3, they both see R1, they both see R2, and they're both going to feed each other, but they ignore each other as their currents go through them. And that's what we call our superposition, and we'll see that again in the solid-state devices when we superimpose an AC signal onto our DC signal. But you just got to make sure you put in your polarities. Watch out, the biggest bully of the block is going to win for the direction. And then just take the difference between the two. If they're both going in the same direction, just add them together. And then you should be able to figure out your voltage. And if you ever do want to double check your work, here's our ground, right? Okay, so what would I measure at this test point A? What would I measure for voltage at test point A? 24 volts. Positive or negative? Negative 24 volts. If I go from here down, I should get a positive 20 or a negative 24 volts. So if you want to double check it, then just go ahead and add up all your voltages as you go. So I come along, these both voltages or these both currents went the same direction. So the first sign I see is going to be negative. And it's going to be a negative, how many volts? Negative 20 volts. Plus, this current is going this way, so I'm going to have plus a negative, how many volts? 4. Negative 4 volts. So that gives me a negative 24 volts. If I even go all the way through that other power supply, if I go from here, first sign I see is a negative 20 volts plus a negative 16, that gives me what, a negative 36 volts. Keep on going, then I got a positive 12 volts, gives me what?
Negative 24.
Negative 24 volts. So always double check your work. It doesn't really matter. So if it works out, just treat everything as a test point. What would I measure from a voltage reference to ground from here to ground? I should get a negative 24 volts. If I go around and go any path, I should still get a negative 24 volts. So there's always ways of double checking your work and making sure that you're doing it right. If you don't get up those answers, then you probably know you didn't do it right. Then then at that point ask the question, see somebody else, and see how they did it, and see where you went wrong. All right, so we'll do the simple. Well, I shouldn't say simple. Not simple for others. But for others, so the quiz tomorrow for parallel circuits. Okay, just then they need to understand current paths and polarities and understand currents. So we'll do that in the morning. Some of you guys will only take you about 15 minutes to do it. Then we'll go into lab and start working on lab. So then I think so. What we'll do is we'll do lab rest of the day tomorrow after the quiz, and we'll do labs on Monday and Tuesday, and then on Wednesday we'll do a lecture for troubleshooting and talk a little bit about the Wheatstone Bridge. All right.
Part of the read the studio.
Yeah, don't forget to put your eye clickers back.
Try to read chapter 5 for the parallel.
Yes, that would be good for review.
It's not going to be a